Okay, I think we'll get started. So if you're coming from the GNL project, I encourage you to look at the introductory video to this playlist to make sure this is the right course for you. Otherwise, we're going to fill in the last piece of the puzzle here for this connection between linear motion and circular motion. And there's this nice analogy between the two and some connecting equations. And that's been kind of the story of the past few days as we've built our understanding of circular motion. So let's just, before we jump into moment of inertia itself, which will be filling out this last bit here, let's remind ourselves of what we have and kind of see how this is all going to fit together. So we're talking about motion around this circle, and we define from in terms of a vector, a magnitude, and a direction, we define counterclockwise as positive and clockwise as negative. So as measured from the conventional angle here, the x-axis. So we would say this distance is positive, and so our arc length here, S, is our arc length. That would be measured from here to here, and so that's the distance if you were to take a string from here to here and then stretch that out. So it isn't linear in the sense that it's curving, but when we talk about this linear connection, we're talking about just this as a linear distance. So you can imagine putting a string there, then taking the string out, and that's the distance. And then when we apply our kinematic equations and force equations for motion along a linear path, then that's what we're talking about here. We're arcing on this arc path. Then this is also given to us by the angle between the radius from the center to where we're at, and then the conventional x-axis. And so the angle theta, the angular position, is another way to indicate where we are along the surface. So the connection here between position and angular position, so x, y, in this case s, is this equation here. And notice I've taken the vector signs off, and because our understanding here now is that this is connection for this special motion where we've defined the directions as I just discussed there. Okay, and then we have all of our kinematic variables, velocity and acceleration, and then there's a corresponding angular velocity and angular acceleration in very much the same way. So angular position is playing the role of position throughout all of this, and then we get our various formulas for velocity and acceleration coming off of that. And again, we have our connecting equations here, and notice the commonality. The angular piece is leveraged by the radius. So if we're traversing this angle, if we're on a long radius, then our arc length has to be much further, say the tip of my finger is much further than if I'm on a short radius over the same angle. And so therefore the velocity has to be faster, the acceleration has to be more if we traverse this in a certain amount of time. Okay, well that's our kinematic variables here. And now let's get mass, right? That's another important parameter because that's going to connect us to force via Newton's law. So we have mass, force, and Newton's law here. Well, what do we have in the rotational case? We have moment of inertia, which we'll be talking about now for this lecture, and then we have torque, and then the corresponding Newton's second law for angular motion here. So we have, again, just everything has its analogy here in this angular case. Now let's look at the connecting equations here. A little bit different. Notice here we had the angular bit over here, the linear bit over here, and it was the angular bit being leveraged by r. Well, now the script flips a little bit. We have the linear piece over here, and it's a kind of a stretch to call it a linear piece, but the piece that shows up most prominently here in the linear equations, mass, is leveraged by, we're going to see the radius squared here to give us this idea of moment of inertia. And then the torque, we saw that last time, is the force leveraged by the lever arm. So the force has to be pointing in a direction that facilitates rotation. And we saw that we have an alternative equation here that we can take the radius, but then only the component of the force that is measuring the, or that's creating the rotational motion. Okay, so that's kind of the outline of the big story. And so again, we're going to fill in this last gap. And so I'm going to erase the board, and we'll come back and look at moment of inertia. Okay, so let's set up just a simple system here where we have a pivot point and some radius r and a mass m, and we're going to apply a force here. Now, throughout here, we're going to consider the force that's only causing the rotation. So in all of this, there may be a stuff you have to do at the beginning of the problem to determine, oh, my force isn't quite at the right angle. I need to find the component of the force that is causing the torque. So we're going to assume that's all done, and we're working here now with only the force that's supplying the rotation. Okay, let's pull our equations from what we saw just a moments ago. And again, this should be F, either R lever arm or F perpendicular, but we're going to assume here now all the F's are perpendicular. So we have these three equations. So let's combine them, and we'll take this top equation. So we have tau equals R, and then MA, and then plug in the A here. So we're gonna plug this in for A, and then we're gonna plug that in for force, and we get this. And this is all we need. This is all we would need. But because this will show up all the time, we define it as something. So we define this quantity, r squared m, because it's going to be the key multiplier that connects force to acceleration. We call that moment of inertia. So that is the definition here of moment of inertia. Now, if we know that the torques will add vectorially, so two torques trying to move the other different way will partially cancel each other out, or if they're trying to rotate in the same direction, then they'll add together. So we have to think about direction, but in considering direction of rotation, we add, and they'll either add as a positive component or a negative component. And so we can write the total torque as the sum of all the individual torques. We can then write each individual torque as M1, R1, A1. So we might imagine so what is the A? So let's say we had this situation where we were pushing with a force here and pushing with a force here. We would be, when we're considering the R for this force, it would be this far. When we're considering the R for this force, it would be this far. So this would be like R1, this would be like R2. And then when we're considering acceleration, the acceleration would be the point, this point, at this position. Whereas the acceleration for A2 would be this point at this position. So there's a different linear acceleration depending on where we are on this arm. Or we might have a situation where we have this, say, connected body of various different masses under gravity, for example. And they would be experiencing different forces, different masses, different radii, and different linear accelerations at their different positions. But in either case, when we go to the angle, they'll all be traversing the same angle because they're all stuck together. So what we can do here now is pull out angle and just leave behind mass times radius and then the individual radius of each of these pieces. So we get a sum of all the individual mass squares and r's, or masses in r squares, and that total sum then for this apparatus is the moment of inertia. So when we have more than one torque or more than one, say, part of the system, then we have to account for that in our definition of moment of inertia. So in summation notation here, so summing over all the individual components is the moment of inertia. Okay. Then we see that the net force is that total moment of inertia times the angular acceleration, and that's just the second law for rotational case. Now, there's a table in the book, and we'll talk about this in the in-class session, but there's a table in a book with all sorts of different shapes, and in principle, you would need calculus. It's a kind of a classic calculus problem to figure out the moment of inertia of a solid piece like a bowling ball or a disc or a rod. The table 7.1 has the common ones of these, and so we will be referring to this. So if you're working the problems and it looks like you're missing a piece of information to figure out moment of inertia, then you should go look at this table in the book. Okay, let's think about pulleys, and then we'll do one example to finish things off. So let's set up a pulley here, and we know that pulleys can redirect the force on the rope. So we've got this pulley here. There's the pivot point of the pulley. We can think about it that way. And here is the radius of the pulley. We'll use a capital R for this. We always assume in a pulley that there's no slipping of the rope. So as the rope moves, the pulley disc turns. And so if we hook this up to a mass, we could see this mass drop and rotate this disc. So this falling mass, this falling in a linear direction, because of this rope pulley system, will initiate a rotation of this pulley. Now in the past, when we ran into pulleys, we just ignored the mass of the pulley. Well, in this case, we would have to include the mass of the pulley, right? And then we would go to this table and look up, if this was a disc shape, we would look up what's the moment of inertia for a disc. Okay, so now we're able to handle pulleys, real pulleys that have actual mass. Okay, some of the parameters here, the rim speed. So that would be like if you were a little ant sitting right at the rim of that pulley. How fast are you going? Well, because there's no slipping here, you're going to be equal to the speed of the rope at which a point, if we just put a point on the rope, how fast is that? What's the velocity of that point? And then likewise with acceleration. So if the rope is accelerating, the pulley must be accelerating. So if we have a linear acceleration of the rope, then the pulley will have an angular acceleration. Okay, well, let's look at an example of a free-falling winch, and that's basically a pulley. It's just that the rope is wrapped many times around. It's got this freely spinning cylinder on an axle. We'll say the cylinder has mass m. Oh, and I should have some radius r here. So the mass is like, maybe this is a big brass piece or a stainless steel piece, and then this distance here, that's the radius, from the axis out to, so perpendicular to the axis out to the surface of the winch. Then we'll use small m, lowercase m, for the mass of this mass tied to this rope, and we're just going to drop the mass. That will start to fall, and it'll spin that winch. Okay, so let's draw the free body diagram for this mass. There's going to be a weight force, and then there's going to be a tension force from this rope pulling up. And we know just from the setting of this the physics here that the tension force is going to be less than the weight force, because we're going to accelerate downward, just with our common sense here. So we can talk about the force in the y direction is going to be by Newton's second law, ma, but also as the sum of the forces, tension minus the mg. Okay, now what about the torque? The torque on this guy is going to be the radius times the force, right? So that's torque. Where do we have that over here? Right here. Right, so we're using this. What's the radius? It's capital R. What's the force? T. Now, are we certain, we should check, are we certain this is a force that's gonna, is the tension always directed in the rotation? Well, if we look at the picture here, and we go, we come out to here, the first contact point of the, well, actually I should go here. The first contact point of this rope, that's where we determine, that's where the tension is acting, right here. This is where the tension is acting. So it is acting, it is indeed acting perpendicular to the radius. So the tension force is acting perpendicular to the radius. Always straight down here, and the contact point is straight across. So all of the tension goes into rotating the winch in this case. Okay, so let's rearrange the Newton's second law. So this is just Newton's second law right here. We'll plug in the tension, right? So this is going to get plugged in here to give this. And then this is from, that's from the table. So that's what a cylinder's moment of inertia is. That's the formula for it. So again, this would be coming out of the blue, but it's from this listed table. And then we can rearrange this into here, so we can get our angular acceleration in terms of the parameters of the winch, the mass and its radius, capital M and capital R, and then the tension applied to it. Okay, so now let's look at the connection to the angular, or to the linear acceleration. So the acceleration of the mass here, and we can write that as alpha times r. So that's over here. Now we have a minus sign in here because we're wanting to be, because we have the rotation and the mass, we can't just say, okay, drop the signs and just counterclockwise, clockwise. We have to be thinking about everything together. So the mass will, the acceleration of the mass will be negative compared to the rotation of the winch, because this is going to rotate clockwise while that is going, or counterclockwise while that is going down. So that's what this minus sign is for. And that's just coming from your physical picture. Had we rotated this the other way, then those two would be the same. Okay, so let's plug in now this into here, and we get this, and then we'll simplify. We can cross out these r's, and we get that. And so our tension is given to us by this equation. Okay, let's go back to our force equation. So F equals ma, but it also equals the sum of the forces. That's coming from our free body diagram. And so we have this. Let's plug this in for tension now. And then let's solve for the acceleration of the mass. Negative 9.8, right? Negative g over 1 plus capital M over little m. And then there's that factor of 2 is just coming from the shape of the winch. So always good to do kind of a sanity check here and make sure of things. Let's make this an ideal case. In the ideal case, the pulley, or the winch in this case, is massless. So we would take capital M, make that 0. That would go away, and we would have just a free-falling mass. Because again, the ideal rope, no weight to the rope, it would just drop. Okay. Let's take the other extreme. Let's just say we put a very small weight on here, and this is a big, heavy cylinder. You would not expect that weight to be able to accelerate rotationally accelerate that cylinder very fast. So if capital M is much, much greater than small m, then this number becomes much greater than 1, and we have a g divided by a large number which will reduce that acceleration. And so everything's behaving as it should there. Okay, so this is fills in this last piece of the puzzle for the connection between the linear and the angular case. And what that does then is it allows us to take some problems and build a rotational piece and a linear piece. So we have a falling mass and a rotating pulley. So it's a good connector then. It expands the types of problems we're able to do.